Today I will talk about GRASP, which is actually a 9 design principles or patterns from object-oriented programming. So the first one is creator, which tells us when should class A create class B. So it's usually when it contains it, when it saves the file, when it uses it, and when it has sufficient data to create it. So let's see an example, a bad example first. So if you have a computer and it's created with processor and hard disk drive, which we have here, it's only simple constructors. So computer is created like this, and then the user is actually forced to instantiate the processor and disk on his own in main method, and then create PC and print something out. So it's a bad practice. Rather, the computer class should instantiate those other two, and the user should only pass some parameters inside. So it's created like here, we have just double and integer, which are speed and size, and then the computer class instantiate them. And the computer is created just with some parameters, and then it's printed out. Like this is the result of the first one. And here is the result of the second one. It's exactly the same as we. Okay, so the next one I want to talk about is low coupling, which means that we should not make components that depends on each other. So if we change one, those changes doesn't affect the other one. Like if you want to make a list of processors and age in drive disks, this is a bad example. Again, we can do it this way. But if I want to add a new disk here, I will have to do it here and then update the constructor and then put a line of code here and few lines here. So this is a high coupling situation, and it's a very bad thing because this is not then reusable. So this can be fixed with polymorphism. We can create something like component, and the processor and hard disk drive can now extend the component, and we can distinguish them by this type. So we can just make an array list of those components and display them with a for loop. So now to add another hard disk drive, we only need to create it here as a component and add it to the list, and it will automatically be printed in this loop, and we can see the results down here. So here it is. Next one is information expert. So imagine we want to count all the disks here, but and we have to find a component that has that information to be given that responsibility. Like computer cannot be the component because it only knows about its own disks, but list is the real component for it. So we can implement a function here, and then we can run it, and it will say we have two disks. But for example, if we want to make some calculation about performance based on processor speed and disk size, we should do it in computer component because that's computer have those information about the specific processor and disk. Now high cohesion, it's actually a measure of how focused the responsibilities are of an object. So class should have very few methods, and they should work with other classes to fulfill a task, but we should keep them simple. Like list components, it has high cohesion because we can see it only adds something here and we then print it out, but it actually just adds those components here with help of component. But maybe for this I have another example. So if you want to build a calculator, we can have an input object in here, add, subtract, and display. So this is bad, this is low cohesion because user interface, which is input and display, is mixed together with logic, so it's a bad practice. So it's better to have input and display separated from logic. Next one is controller. So we should ask ourselves here what object is going to stand between user interface and coordinate operations. So it will take instructions and distribute them to appropriate components. So this is a too small application to demonstrate it. So I will give an abstract example. Like if we have a controller and user chooses some processor and disks to build computer, Then controller would be like, if there was some search component, it would be like, hey, search component, see if these components exist, and then if they do, then send it to computer, and he will build a computer and give it to me so I can give it to our users. So that's how it should work, imagination. But again, this is a very small application to have a controller implemented. Next is polymorphism, which means that we should dynamically handle numerous tasks for similar object types. So for example, if we're buying a processor, we have AMD, which gives us information like this, and Intel, which give it like this, and we need a processor price, but we doesn't want to make separate functions for this, so we can use polymorphism, make an abstract class. Abstract means it can be instantiated, and it will have this method, which we can then adapt to the components that are actually different. Next is pure fabrication. So it basically says that if we have something and we don't know some responsibility and we don't know where to put it, who to assign it to, we should create a new object, because it's better to create new one than in order to keep high cohesion and low coupling everywhere. So like, for example, if I want to make a switch currency for some AMD processor here, I should not do it in AMD component because it breaks high cohesion. That's not in our interest. I should not do it as well at get processor price, because here it will be like high coupling situation. It will become dependent, and so the best thing is to make a new switch currency class. Then we can call it whenever we want to switch the currency. Indirection is technique used to avoid coupling between objects by separating them with an intermediate object, which we call adapter, and we are again using polymorphic techniques. So here we have a change component like in a computer, and it has this change method. So HDD we can change it simply like this, but like, let's say processor, we need to do something complicated, and it cannot be just the change method. So we are going to implement adapter that will actually have a change method, and it will then call the processor method that it needs to be changed. So we can treat this processor and disk equally, even though their change methods are not equal. So we can then check with this adapter tests, and yes, so both are changed, as we can see, and they are called like only these change methods here. And the last one is protected variations. So we should locate elements with coupling that could possibly change in future and protect ourselves from those changes. So for example, if Intel sometimes gives info like this and sometimes just like this, we can implement a protect class here. So it will check how the information is given. It's a really banal example, but it should show how it should work. So this is new get processor price method, and we create an instance of protect object here and give him this information. So he will work around it in a way that if here is Intel in front or it's not, we will always have a real price. So we are protected from the possible variations of this parameter.